Hi, everyone. Welcome to this episode of Demo Deep Dive. I'm Rohan. I'm part of the OpenShift team and now the demo team. And we are here with Christopher Nuland. Now, before I get into Chris's role at Red Hat, I just wanted to welcome you to the show. So what we do in the show is we just deep dive into some demos that are created by our technical marketing folks, skilled technical marketing folks. Let me add that. And so at the top of your screen, you have a little scan QR code where you can, do this demo while it's being demonstrated. And yeah, nothing much to add there. We'll just go through the flow, and you can join us. Feel free to drop any, messages in the chats. But today we have Christopher Nuland, so Principal Technical Marketing Manager for AI at Red Hat. So you're in great hands because he's been in the industry for a while, right, Chris? So would love to hear an intro from you as well, and just a little bit about your time at Red Hat.
Yeah, definitely. So, my name's Christopher Nuland. I'm a technical marketing manager, specifically focusing around AI inference. And I came to Red Hat. I've been actually at Red Hat for a while now. I think I'm going close to my 8th year. And I originally was part of a team that was brought in to do work on metrics-driven transformation. So my background is a little bit of AI and math and computer science, and had this kind of long journey of doing things with like containers, doing simulations for the US government, and kind of slowly making my way to what I'm doing here today. And from the metrics driven transformation side, I started getting really interested in how AI workloads run on platforms like Kubernetes and OpenShift. My degree was actually focused around AI. I didn't immediately start applying that degree. I went more into the systems side, but it was it's kind of fascinating to see that evolution, and I've been able to be a part of that from really getting started with big data back in the 2010s with data lakes and Spark and other things, to the point that we're at now with more generative AI focus. So my focus on this particular team for AI is specifically around LLMD and VLLM. So really core AI inference. How does your model actually leverage your AI compute, your AI accelerators like NVIDIA, Intel, AMD? And that's what I'm excited to be here today to talk about, actually, one of our new projects that'll be integrating into Red Hat AI 3 integration into for OpenShift AI here pretty soon.
And how relevant your degree has become in today's tech age, right?
Well, yeah. So fun story there. It was my junior year, and my advisor basically told me that this degree was going to go nowhere. She said, unless you get a PhD, like you're going to be working at Starbucks, basically. So my junior year, I actually switched to focusing on systems integrations. So focusing more on like Hadoop was really popular. It was just getting popular at the time when I was in college. Spark, the concepts of Spark were kind of coming out of that same area. And I did finish the focus on both because I still loved AI, but my career really took me more in the systems direction rather than the AI side, because at the time it was really seen as more academic. So crazy how things have changed.
Definitely. And now you're here, part of this new business unit that we've created at Red Hat.
Yep.
It's focused on that, and Red Hat being an AI company now and one of the leaders in the space. Great to have you here to just talk us through LLMDs and VLLMDs. So
Yep.
this was one of our very high performing assets on our Interact page, actually. So that's why we have the creator for you guys here today. So as I mentioned, scan through and just give it a shot. If you have any questions, drop it in the chat. But I'm going to hand it over to Chris. And so Cedric is also a part of your wider team, and he's also an active creator. So
Yes.
he may join later in the call, but I will leave it to you to just talk through all of this, and then we can sync up at the end for some questions that we have from the field.
Definitely. And just a note too that Cedric actually helped me put this together. So I did the actual demo portion, but as I always tell people, he's the guy that makes it look pretty. So I do the experimentation. He takes the experiments and actually puts it into this neat format. So I definitely want to call out him for all of his hard work that he does for my team and how he's helped me put this demo together, which I'm excited to share here.
Perfect. So what are we looking at today?
Yeah, so let's talk about LLMD. This is a really exciting project. I'm so excited about this project that I'm actually starting now to contribute to the project. It's the first open source project that I've really joined from the community side in a few years, just because of how excited I am about it. I think it's solving a really needed problem. So let me kind of talk about where this project came from. The problem that we're trying to solve here is that traditional inference, when you put it into something like Kubernetes, like OpenShift, for example, it treats AI very much like it treats a traditional application. So the application has routing based off of CPU usage or memory usage, HTTP requests. It could be round robin. It could be sticky sessions. What we find is that this isn't a really effective way of doing AI workloads. AI workloads are more interested in GPU consumption, time to first token, cache hit rate. These are all like new metrics of a new paradigm that doesn't fit well within the old application paradigm. And this is where LLMD is really trying to fill the gaps, both from a routing standpoint, like I just mentioned, and also from a scheduling standpoint within your cluster. So this project came about earlier this year. It came out of the VLLM community. VLLM is a community project focused on the inference of AI models, mainly generative AI models, that is leveraging things like KV cache ability, so the ability for your prompts to kind of remember what has been previously asked to kind of speed up the responses, and then also take advantage of things like RAG technology. And I'll talk a little bit more about that here in a second, how that's relevant to the project. But a lot of these like key members of the AI community, like Google, Red Hat, NVIDIA, IBM, they came together and realized we have this problem. Can we solve it? And they realized that VLLM wasn't really the right home to solve it because VLLM runs on a single server. It runs on Kubernetes. It runs in a variety of different types of platforms other than just at scale. So LLMD is really here to talk about LLM inference at scale, really a distributed LLM inference. And what does that look like? So that incorporates those main companies I mentioned, but it also has other organizations like Hugging Face, Mistral, CoreWeave. There's a lot of these organizations now that are contributing to this project. How does LLMD deliver this? Think of it as if you're familiar with how software worked in like the aughts. It was very much client server based. You had a single server. If it failed, um, you were done. Like you had to wait until the server came back up, you fixed the problem. We didn't really have this idea of like distributing software back then. And also the applications were single applications, what we call monolith applications. LLMD is very similar to this concept of what we call microservice based applications. It's breaking up the applications into smaller parts. So if one component fails, all the other components are still up, and then distributing those over multiple machines, like with what we do with an OpenShift. And what we find is that the LLM actually has multiple layers. It has multiple sections of how it solves for its output. And what we do with LLMD is we actually break that apart. And I'll show some examples of that here soon. By breaking it apart, though, it allows us to then have more observability over those different parts. We now have a better idea of cache hit rate. We can scale certain components of the LLM based off of more need. So certain workloads are going to be prefill heavy, certain workloads are going to be more decode heavy. I'll talk about kind of what those two are here in a moment. But the cool part of this too is that once you break up the LLM, you can now assign it to different computes. So the prefill, which I should probably go into what the prefill and the decode is first. The prefill of an LLM is when you first send your prompt. And the best example I can give is if you're asking for a summary of a document, like a large PDF. Well, that entire PDF is going to get injected along with your question. It'll be tokenized and then sent to the LLM. And it's going to go continually over all this information over and over again until it's built relationships within this and then applies that into the cache. This is what we call the prefill. This is what happens before you see a response from popular tools like ChatGPT, for example. And the important metric tied to this is what we call time to first token, the time it takes for you to first see that response. The decode side is what you're seeing when the LLM is talking to you. It's giving you a reply. You see it kind of chatting on the screen. Each iteration of that chat is what we call the throughput of, or the latency of the decode. And what we find is that certain workloads will favor certain sides. For the document analysis, like that prefill is very large, but for a simple chat application that's not actually having a lot of like RAG context, we may not see as much from that prefill. The decode side is also very memory intensive, and if you have a lot of users, you may want to actually scale out your decode further than your prefill. Traditionally, this was all done in a black box within a single container or single pod, and you had to scale that same footprint every time that you wanted to create a new instance of the LLM. Well, now you have the ability to scale these components individually. And what we find is that this is extremely optimal when we start assigning GPU. So what we have here, like before, we have like a traditional LLM. Well, now we have this approach that is breaking everything apart to its prefill and its decode. And also, it now has what we call the inference gateway. The inference gateway is prompt aware. So instead of routing based off of CPU or round robining or sticky sessions, it actually knows the question that you were asking the LLM. And this allows it to look at the prompt logs, or the stack in this case, and be able to actually send your question to the appropriate instance, the appropriate cache, to optimize that time to first token. Because if you've asked that question before, essentially like summarize this document and it's a popular document within your organization, well, more than likely someone's asked that before, in which case it doesn't have to go through that lengthy process again. It can just pull from that cache. Well, now, if you did round robining before, you had maybe a 1 in 3, 1 in 4 chance, depending on how many instances you had, to hit that cache. Well, now you're guaranteed to hit that cache because now you have smart inference that actually knows it's prompt aware. It's what we call prefix cache aware as well. So it can actually make those routes effectively. And there's a lot of other cool techniques now that we can do by having this inference gateway being able to be really making smart decisions on how it routes to the individual LLM instances. So let me show you a demo of what this looks like. Here we have the topology of the llm-d demo namespace that I've created. We'll go ahead and like show some of the components here just so you can see what's going on. I said this breaks up into the prefill and the decode. In this instance, we have 3 decode pods. So in this case, we've got, like you can see here, we have the 3, each of them having their own, they have a shared KV cache, but depending on how you configure it, you could have individual KV cache as well, depending on if you want the like a wide type of model, which we'll talk about here in a moment, or more singular types of models. So this gets into more like mixture of experts conversation, where certain parts of the model might specialize in different areas, or you may have different types of models that have different types of KV caches associated with them. Really just depends on how you want to integrate the routing in this case. And then down here, we have what's called the EPP. The EPP is a component of the inference gateway. It's what makes the decision on how to route. It's what is KV cache aware. So the stack of all the previous prompts that then relate back to those cache inputs are kept within this EPP instance. So think of it as like one of the core components of the inference gateway here that makes those decisions. The inference gateway is in this demo, it's showing Istio, but really it can be any kind of Envoy-based type of gateway. So there's a few, like K Gateway, I think is another popular one that's used a lot. For us, for this demo, we're showing how it can integrate with Istio. But really, you just need something that can have access to that EPP decision maker. And so this is the conjunction of those two is what's making that smart routing, that prompt aware routing available to the llm-d stack. So I'm going to do some load testing here. I have here a Tecton pipeline, which this is not a sophisticated test. It's just going to send like thousands of the same request over and over again. This is not like an enterprise-based benchmark. This is, my my Saturday afternoon project of just validating that this is working. But I like showing this because I think it's the same kind of tests that a an AI engineer or a platform engineer would run themselves at first just to get some initial idea of how this is working. So that's why I stuck with this one. I'll show you something a little more sophisticated here in a second. But you'll see here that we're going to hit the inference gateway endpoint, and we'll go ahead and give it a go. We can go into the logs, and you'll see I'm just hitting this over and over again with the same type of request. I do allow for what's called a warm-up period. The warm-up period is allowing that KV cache to form. So I send one request, I kind of wait for a little while, and then send subsequent requests. We find that that helps with the cache hit rate that I'll be showing here from a metric standpoint. So after I ran this, I'm seeing good results. We're seeing that the all the traffic was routed to one pod with a 90% stickiness based off of the prompt. So this wasn't a sticky session, but it was a stickiness based off of the EPP routing correctly based off of what it saw within the prompt. So it knew that this is where the cache needed to be. So out of 4,700 requests, we had those results going to that one pod. And then if we want to take a look at the cache hit rate, we can go into a Grafana dashboard now, and we can see that we had a total cache hit rate of 86.8. So the cool part is if we look below this, we can actually see how this is broken down into individual pods. The reason why it's slightly off is because there was some amount that was actually sent to these other pods, pretty insignificant. You can see it's below 1%. And the reason why this happens is just sometimes that EPP gets overloaded, and you can have different fallbacks. In this case, I allowed fallback, but you could just say, no, don't route, like has to go through the inference gateway completely. It has to be validated. It really just depends if you're using EPP to get a performance increase, in which case you're going to want to allow that pass through when that stack kind of builds up on requests, or if you're using it for some security measures or as a guardrail where you want the EPP to kind of act as a validator before it goes through to the final request. So this is one of the powerful things with llm-d. It's prompt aware. It is, in this case, you're seeing it's routing to this pod the majority of the time, while also getting a cache hit rate of well into the 80s. This is a good cache hit rate. If you actually were to use this in an enterprise setting and do some configurations, and this has been running for days for your RAG implementations and your different contexts that you have built in, you would actually kind of find this probably going up well into the 90s. Like I said, this is more of the weekend warrior demo, but these are still really good results for the fact that I just, kind of bombarded it with the same question over and over again. And the cool part is we can see some of how this then relates back to request throughput, time to first token, how this is doing to the end-to-end request latency. A lot of these metrics that are really important that we now have visibility into much more with a tool like llm-d. If we were to actually do this from a demo perspective, so this is more of like a traditional benchmarking kind of way. I'll go here and I have a variety of questions on like what is artificial intelligence, what are the benefits of renewable energy, some like more science related questions. And what's important here, and let me pause. You'll see our requests start at 6:45, and we'll see that the subsequent requests will actually start going down significantly here. So right now we have a pretty high time to first token. But if we're to continue these requests, and we can see some of the same here when we start kind of looking at another view, we'll actually see that the latency can drop down all the way to 200 and 300 here. When you switch back to load balancing here, I'm going to show you kind of what that looks like. So I turn off the EPP for a little while, and what we see here now is that traffic now is spread a lot more evenly across the two pods. So it shows what happens if you were to disable that functionality with the EPP. That now, when we're starting round robining, we'll see it actually hit multiple pods instead of the just that one. So it's a very powerful tool. Allows you to do a lot. This is just one example of what llm-d can do. We have what we're called 3 well-lit paths. Our other well-lit paths are the disaggregated prefill, which is that breaking those components up into their parts and how that gets scheduled on your cluster. And then another area that's super cool is this area of mixture of experts. These are the large models like DeepSeek R1, GPT OSS that just came out. These are all what we call mixture of expert models. And certain parts of the model get split up. The analogy I always use is like going to a college or university and you have a history question. Are you going to go into the physics building? Are you going to go into the administrations building? More than likely, you're going to go into the history building. And it's the same kind of concept. It's like certain parts of knowledge are broken up into different parts. And then that part is the only thing that triggers once it's been routed to that section of the model, rather than triggering the entire model. And that needs something like llm-d to be managing the distribution of those different components, as well as the routing to where those components need to be once you've made that request to the LLM. So extremely powerful tool. There's a lot of momentum within the community. Like I said, there's a lot of major players who are contributing to this. With the release of Dynamo, which does some similar kind of functionality from NVIDIA, from more of a closed source approach, we're seeing an industry need for these types of technologies. It's what will make hosting LLMs more accessible, especially these larger models like mixture of experts or ones that need more cache routing available to more common enterprise practices rather than just the AI labs that have been running it over the last couple of years. So really cool technology. Like I said, I'm really excited about this. I think it is going to be the next big conversation in the area of AI, especially we see things like AI sovereignty dictating that more and more people need to run their AI models locally or in some type of hybrid configuration where they need to have more auditing control. They need to be able to secure their AI better. They need to be able to prove where it's running. And technologies like llm-d are what are going to make that possible. And that's it. Thank you for having me. This is
No. It completely makes sense. I had to just be quiet and let the experts speak. I think as people are doing the demo with us today, I'm also learning, and they're also very actively listening in. Completely can see it. Almost feels like a no-brainer. But I'd love to ask you, just if you were to summarize just the top 3 benefits, but also the 3 considerations if someone were to move to this kind of process, what would you say they are? Especially the considerations. I guess we can touch on those.
So considerations wise, I would say just be considerate of what type of AI compute that you have. Anytime that you're running this, it takes a good amount of compute. I think what you'll find is that once you move into an LLMD configuration, it may not take as much compute as you originally thought because of a lot of the optimizations that are being made. And I think just know that it is a new paradigm. So you're looking at a new type of configuration or a new way that we're approaching how AI is inferred. So I would just say, be patient with it. Check out the LLMD community page where there's a lot of quick starts and guides on how to deploy models like DeepSeek R1, for example. And be sure to ask the community for help as you're starting to put some of this together. I think from a benefit standpoint, it really does come down to cost is very important, flexibility, being able to kind of manage how you want to scale out your components, and then observability, being able to actually now see a lot of these components firsthand and how this component is using resources compared to this component. It allows us to do a lot more observability, relate that back to like site reliability engineers and how they would want to manage these types of large LLM systems.
Yeah, I mean, just seeing the graphical interface of the Grafana dashboard just makes it easier for people who are just comfortable with those kind of
Absolutely.
yeah.
Yeah. Visual people, it definitely helps now that we're making that more readily available.
Yeah. And so I wanted to ask about just security. It's a really important aspect of this. And you mentioned about the EPP being like having being a validator. But what are other components to this that make sure that it adds that layer of security?
Yeah. So the best example I have is that in Europe, there's this organization. It's a finance institute that does business in multiple countries, but they have to be able to prove that their compute is like their models are running in those sovereign countries. So they have like this very complex hybrid kind of cloud configuration, and sometimes even within the same cluster, there may be data that's from one country sitting next to data from another country. It's just how they have their configurations. LLMD, because we can split these things apart, will allow people to take advantage of the same model weights while having the KV cache split amongst different nodes. So you can say Sweden, for example, the data goes over here, and Finland goes over here. It's more about auditing and AI sovereignty than necessarily security. But then once you put it into the context of OpenShift, then OpenShift brings in a lot of that authentication piece that then can tie into the inference gateway. We have different like RBAC controls. Within the EPP, you could have other types of guardrails set up. Similar to how the analogy I always give to people, as databases started getting more prevalent, you wouldn't expose your database to the public internet. You have multiple layers of gateways in front of it, as well as checks to make sure that the queries that are coming in are valid. It's the same thing with uh, this is the same type of approach that you would have with LLMD with guardrails. So there's opportunities to implement guardrails, I think, in a more optimized way when we start talking about LLMD as well. So there's so many different kind of components that fit into that. But I would say it's really solving a lot of issues of AI sovereignty and auditing when we talk about AI at scale.
Yeah, makes sense. And just my final question before we sign off, just looking at the time as well, but just loving talking about this because we also have a lot of people who want to be able to, find out more about this kind of technology, especially as a Red Hat customer. You talked about the open sourceness.
Yeah.
We'd love to know more about the collaborative efforts we have with those companies, but also how do we compete in this space?
Yeah, definitely. So we are collaborating a lot, like I said, with NVIDIA, Google, IBM, and Red Hat are the main maintainers of the project as well. AMD now has gotten on board as well as Intel. So there's that community aspect. But from a product standpoint, We are implementing LLMD into our Red Hat AI 3.0 launch, which will be incorporated directly into OpenShift AI. So you may not actually see LLMD as, let's say, a product, but it will be implemented into our current products like OpenShift AI, for example, where we'll be leveraging this technology for this type of inference to be able to run within your cluster and have a lot of these optimizations and things built right into the product. So I would say we're, from an open source standpoint, NVIDIA, Triton to NVIDIA compared to VLLM from an open source standpoint is the same as NVIDIA Dynamo to LLMD. So those who are looking for an open source solution that might be, have more opportunities for different types of AI compute integration, I think LLMD then becomes the obvious integration. And then, having it integrate into a product like OpenShift AI makes it readily available to enterprise customers.
I think that's a key point and good to know already for people who might want to explore it if they're already customers or potential customers as well. But great. Any sign-off points, Chris? I think you mentioned like your background and your passions towards this technology and how it's come all this way. But anything, last comments to add?
I think I'm most excited about the observability piece. I think it might be one of the ones that's most overlooked. I think once we start getting this observability aspect into the hands of more SREs and DevOps engineers, I think we're going to see a real renaissance when we talk about how we view AI and how we manage AI in a hybrid cloud configuration. So just keep an eye on that area, because I think it's one that a lot of times gets overlooked for more of the bigger features.
Perfect. Well, thanks for joining us today. And as always, you can access our demos on information.com. And that includes Chris's, and we're definitely going to have you on the show again because I know you're an active demo creator, technical marketing manager. So check those out, everyone. And if you have any other questions or any, niche questions that we could answer here at Red Hat, definitely reach out or drop a comment on YouTube, and join us for the next episode. And yeah, thank you for joining us on Demo Deep Dive. See you next time.
Thanks for having me.